idea of saturation. I talked a little bit about vapor pressure and saturation vapor pressure, and I talked a little bit about a few different types of humidities: absolute humidity, specific humidity, and water vapor mixing ratio. And those, other than the definition, we're not going to talk much about them. But what we are going to talk about is the humidity variable that you have seen the most in your life. Don't believe me? Take a moment, pull out your weather app, look at humidity, and you'll probably see it as a percentage. But what you actually don't know, or what you haven't been told, is that's actually a certain type of humidity called relative humidity. And we're going to talk about that today. I'm going to talk about how it's actually a misleading variable, how we measure it, and then I'm going to end this lecture by talking about a more commonly used, or a commonly used and more accurate variable called dewpoint temperature. So that's what we're going to talk about today. So first, let's talk about what relative humidity is. So relative humidity is simply a ratio of water vapor currently in the air versus the amount of water vapor needed for saturation. It's content divided by capacity. It's simply water vapor content divided by water vapor capacity. And that gives you some kind of decimal number. And to convert that to a percentage, you just multiply it by 100%. And that gives you the relative humidity of the atmosphere. Now, with that said, this is a misleading idea, or relative humidity can be very misleading. And the reason why is because there are two things that can change a relative humidity. You could either change the water vapor content, and this is done by simply changing the amount of humidity in the air, by simply changing the amount of water vapor in the air, or you can change the water vapor capacity. And if you remember from the previous lecture, when we talked about the idea of saturation vapor pressure, that's what water vapor capacity is. How much water vapor can be present in the air before the air becomes saturated? Well, in this case, water vapor capacity is determined by temperature. So really what we're looking at here is the amount of water vapor in the air divided by this thing that's caused by the temperature of the air. And so when changing relative humidity, we're changing one of two things. We're either changing the amount of moisture in the air, or we're changing the temperature. This is different from every other humidity variable I'm going to talk about. All the other humidity variables, absolute humidity, specific humidity, water vapor mixing ratio, dew point, those all change based on one thing and one thing only: the amount of water vapor in the air. Relative humidity can change by that, but it can also change due to changes in temperature. So it can change due to changes in temperature. So a relative humidity is given out as a percent, and it actually tells you how saturated the air is. So if you have a relative humidity of 50%, that means the air is 50% saturated. That means the amount of moisture in the air is 50% what the air can hold. So there are two ways you can change relative humidity. The first way is by adding moisture to the air. If you add moisture to the air but you leave the temperature alone, that will raise the relative humidity. On the other hand, if I took moisture away, if I took water vapor away but left the temperature alone, relative humidity would decrease. On the other hand, if I left the amount of water vapor in the air alone, but I changed the temperature, that would cause relative humidity to change as well. For example, let's say I have a certain amount of moisture in the air. In this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules in the air. So in this case, I have 12 molecules in the air, and the temperature of the air is 20 degrees Celsius. And so our relative humidity is something here. Now let's say I warm the air up to 30 degrees Celsius, but I don't change the amount of moisture in the air. I leave that alone. So we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we still have 12 water vapor molecules in the air, but now the air is warmer. This means that air could hold more water vapor. As a result, relative humidity decreases. The air is now less saturated than it was. On the other hand, if I cooled the temperature down, that would cause relative humidity to increase. Going back to this fraction right here, you have these two numbers. In the numerator, you have water vapor content. Now, if you remember from fractions, from just some of the basic rules about fractions, if you increase the numerator, the total value of the fraction always increases. If you increase the numerator, the value of the fraction increases. If you decrease the numerator, the value decreases. On the other hand, the denominator behaves a little bit differently. If you increase the denominator, the overall fraction decreases. Don't believe me? Let me draw this real quick. So let's say I have two fractions here, 1/2 and 1/3. Which one is larger? Well, 1/2 is larger. 1/2 is greater than 1/3. Right? 1/2 is greater than 1/3. So the smaller denominator results in an overall larger fraction. So, and that's just a review of fractions. But the idea is that if we increase the capacity but leave the content alone, that causes a decrease in relative humidity. And the way that we change the capacity is by changing the temperature. Now this actually leads us to a pretty interesting fact. Let's assume for one moment that the amount of moisture in the air, that vapor pressure, the content, does not change. However, so over a 24-hour period, the content does not change. But the temperature does change, like it does every day. How would relative humidity change throughout this 24-hour day? Well, the fact of the matter is, if content stays the same, the relationship between temperature and relative humidity is an inverse relationship. What that means is that when temperature goes up, relative humidity goes down. And when temperature goes down, relative humidity goes up. And if I were to plot relative humidity on here, what you would actually notice is that it is the exact opposite curve. It looks like this curve, but it's flipped over. So, and I'll go ahead and do that right now. So let me draw that on here. So let's just say that relative humidity it starts right here at midnight. And then as air temperature decreases, relative humidity increases. Why? Because the denominator of that fraction is getting smaller and smaller and smaller. And remember, the smaller the denominator, the larger the overall fraction. On the other hand, after 6 a.m. on this graph, air temperature begins to rise. In this case, relative humidity will begin to decrease. And it'll continue decreasing as long as the temperature rises. It'll continue decreasing until the hottest time of the day. At the hottest time of the day, relative humidity will be at its lowest. And then as air temperature begins to cool again, relative humidity will go back up. As air temperature begins to cool, Relative humidity will go back up until midnight. So basically, relative humidity is oppositely, inversely related to air temperature. Make sure you understand that a lot of people think that the two are directly related, but they're inversely related. So write this down in red ink, double underline it, guarantee you'll see it on the test, on the midterm, on this next quiz. You'll do this in this next activity. Guaranteed, write this down. As air temperature rises, relative humidity decreases. As air temperature decreases, relative humidity rises. So, again, as temperature goes down, like it does right here, relative humidity goes up. As air temperature goes up, relative humidity goes down. And we see this on a daily basis. And this is why we see dew on the ground in the morning. Because in the morning, air temperature is at its coolest. And so relative humidity is at its highest. This isn't because moisture suddenly blew in at night. Believe it or not, the amount of moisture in the air doesn't really necessarily change that much throughout the day. Unless a dry air mass has moved in or a moist air mass has moved in, assuming no advection of moisture, no moisture is moving in or out, assuming that that stays the same, the only thing that affects relative humidity is air temperature. And so we usually see a relationship like this. When temperature goes down, relative humidity goes up. When temperature goes up, relative humidity goes down. And this isn't just something theoretical. Believe it or not, you can actually see this in everyday plots. I actually have a weather station at home, and I always like to toggle between the air temperature and the relative humidity graphs, and they're basically the same graph, just upside down. They're basically the same graph, just upside down. And so this right here, this is data that I took from San Jose International Airport, right down the street from where I'm recording this. And what it shows is this red line over here is air temperature. This green line on the right-hand graph is relative humidity. And again, what you notice is that when air temperature is at its highest, relative humidity is at its lowest. Now there's another green line on here that I'm going to talk about in a second. This is a really important green line. This is what's called dewpoint temperature. I'll talk about that in a few minutes. So, as I mentioned earlier, all the other humidity variables that we talk about in this class do not change with temperature. They only change when you add or remove moisture from the atmosphere. Relative humidity, on the other hand, changes with both. So how do we as meteorologists even measure humidity? Well, I mentioned in the first lecture of this module, way back in lecture 11, that when humidity changes, our bodies actually have certain things that are sensitive to that change, namely our hair. When when relative humidity gets higher, when humidity gets higher as a whole, this causes the length of our hair to change. And this can make our hair curly. That is one way we can measure humidity. Another way we can measure humidity is by using a device called a sling psychrometer. And a sling psychrometer, and I'll come back to the slide in a second, looks like this. So here's what's happening here. You have two thermometers connected to a pivot. One of the thermometers, the bulb, is covered with a cloth called a wick. The other bulb is left exposed. Well, here's what we do. We actually dip this cloth and the bulb with the cloth in water. And we call that the wet bulb. And then what we do is we take this pivot and we swing it around. This causes these two thermometers to rotate, and they begin to swing around and swing around. Well, what's going to happen to the moisture, to the water on this little cloth as we do that? Well, what's going to happen is it's going to begin to evaporate. This takes us back to talking about latent heat. As the water evaporates, what is that going to do to the temperature of the air surrounding the water? Remember, when water evaporates, it cools its surroundings. Again, that's why you feel cold when you get out of a pool, or that's why your body even sweats to begin with, because it cools your body. The evaporation cools your body. So when water evaporates off this wick, that causes the temperature in this thermometer to decline. That causes the temperature to decline. Meanwhile, the dry bulb, the exposed bulb, that doesn't have any water on it, isn't going to experience a temperature change as you swing it around. Why? Because there's no latent heat release, there's nothing really going on, it's just getting dizzy. The thermometer is getting dizzy, I guess. Well, what actually happens is, depending on how moist the atmosphere is, a certain amount of water vapor will evaporate, or a certain amount of water will evaporate off this wick. If the atmosphere is really, really moist, just like when your body sweats and it's really humid outside, the sweat can't evaporate, the moisture won't be able to evaporate off this wick. Therefore, the temperature will not decline much. And the difference between the wet bulb and the dry bulb is very, very small. When this happens, relative humidity is really high. Why? Because the air is close to saturation, water can't evaporate off the wick, so the difference between the wet bulb and the dry bulb is really small. On the other hand, if the humidity of the air is really dry, it's really low, that means that moisture will easily evaporate off that wick. That means a lot of moisture is going to evaporate, more latent heat is going to be absorbed by the water, that's going to cool the atmosphere even more. This temperature will be much lower. And in this case, the wet bulb temperature will be much lower than the dry bulb temperature. When that happens, when the difference between the two is really large, that represents a really dry atmosphere. So again, going back to this idea, you have two thermometers. One is dry, we call that the dry bulb. The other has a cloth, that little wick on it, that's called a wet bulb. We dip the wick in water and then we swing the thing around. As we string it around, that causes the water to evaporate, cooling the temperature on the wet bulb. The drier the air is, the more water will evaporate, the cooler the temperature is. And so the greater the difference between that dry bulb and that wet bulb, the drier the air is. If the air is really moist, we don't really get a whole lot of drying. Another instrument we can use actually goes back to that whole hair thing. We can actually take an object that's sensitive to changes in humidity, like human hair, and we can actually use that to record changes in humidity. And we can then use this to record changes in humidity. These types of instruments are called hygrometers. And the way a hygrometer works is you have strands of hair, usually either human hair or horsehair, and as the humidity changes, these strands either become a little bit shorter or a little bit longer. That causes the amount of tension on this contraption to change. That causes this needle to either rise when humidity is higher or fall when it's lower. And as this drum is spinning and this needle is rising and dropping, that could then record changes in humidity. Now this is very low tech, and to be honest with you, most modern day humidity sensors don't use anything like this. They use different types of metals with conductivities that change due to humidity, or they use, there are many different ways that we can do this, like different coils of wire. So there are different ways that we can do this. But the idea is that we have something that is sensitive to changes in humidity, and we identify how that something changes over time. And that can then give us a measurement of humidity. So that's pretty cool if you ask me. I mean, we can actually just look at how humidity changes by looking how something like hair changes. Now, the last thing I'm going to talk about in this lecture is dew point temperature. Now, write this down in your notebook or on your notes or anything that you have next to you. Dew point temperature is not air temperature. They are two different things. Let's talk about how they're different. Air temperature is the current temperature of the air. Dew point temperature is the temperature that the air would need to be cooled to in order for relative humidity to reach 100%. Dew point temperature is the temperature that air needs to be cooled to in order for the air to become saturated. So again, think about what I said earlier when I said warm air holds more water vapor than cold air. And as air temperature goes up, relative humidity goes down. But let's assume that water vapor content doesn't change, so that numerator in the relative humidity fraction doesn't change. But we begin to cool the air. As we cool the air, the capacity of water vapor, that water vapor capacity, begins to decrease. The denominator in the fraction becomes smaller. So the overall value of the fraction becomes higher and higher and higher. And eventually, if the air cools enough, the air becomes saturated. The temperature at which this happens is called the dew point temperature. So the dew point temperature is a theoretical temperature. It's the temperature that the air would need to be cooled to in order for the air to become saturated. So it is not air temperature. It's the temperature that air would need to cool to in order for it to become saturated. It's kind of similar to wet bulb temperature, that temperature of the thermometer with the wick on it. But they're not the same. There's a few reasons why they're not the same. But you notice at night, as the air cools, dew will begin to form on the ground. And the reason why this happens is because the temperature of the air right near the ground cools to the dew point. It cools to the dew point. The other thing that dew point is useful for is it's a good indicator of how much moisture is in the air. When you have a high dew point temperature, that means there's a lot of water vapor in the air. When you have a low dew point temperature, that means there's not as much water vapor in the atmosphere. Make sure you know that too. So first off, dew point temperature is the temperature that air needs to cool to in order to become saturated. And higher dew point temperatures mean more moisture in the air. Low dew point temperatures mean less moisture in the air. But again, the dew point temperature does not change unless you add moisture to the atmosphere or remove moisture to the atmosphere, or you remove moisture from the atmosphere. And this doesn't happen throughout the day. This isn't a diurnal cycle. So a diurnal cycle is simply a cycle that changes throughout the day. This doesn't happen like that. The only things that change dew point temperature are advection of moisture. And that doesn't necessarily have a daily cycle to it. So, just to give you an example, if you take a look at that relative humidity versus temperature graph that I showed earlier, temperature goes up, relative humidity goes down, temperature goes down, relative humidity goes up. This line down here is dew point temperature. And if you take a look, the dew point temperature doesn't really change much during this time. This tells us that the amount of moisture in the air doesn't really change much over time. So that's really what this means. When dew point temperature stays the same, that means that the amount of moisture in the air is staying the same. Even though relative humidity is changing, these changes in relative humidity are mostly caused by changes in temperature. Now, on the other hand, if we noticed a big drop in dew point temperature, we would notice a subsequent drop in relative humidity. Why? Because a lot of moisture has just been taken out of the atmosphere. You'll see an example of that in this week's activity. But again, the dew point temperature in this particular example isn't really changing much. Therefore, the amount of moisture in the air isn't really changing that much, and the temperature at which saturation would occur isn't really changing much. The last thing I'll show you is a couple of maps, and these are maps of the United States. North is at the top, south is at the bottom, and this shows you dew point temperatures, average dew point temperatures over the entire country. Higher dew point temperatures represent areas of more moisture. And I think you kind of notice that naturally, the areas of higher dew point temperatures, those are the areas that are shaded in greens. Those are actually either along the coastline, over here, or over here in the deep south. And if you remember, air down here is very moist. On the other hand, areas with very low dew points, very dry regions, are mostly inland. They are mostly inland. So here the highest dew points are down here in the deep south, near Miami. Meanwhile, lowest dew points are over here near Seattle, Los Angeles, San Francisco. Or sorry, these are also high dew points, I lied. So highest dew points here and here. Lowest dew points, far interior United States. Fargo, North Dakota, Denver, Colorado. These areas are very dry in January. Now watch what happens in July. If you notice in July, two things actually happen. One, overall dew point is much higher pretty much everywhere. The reason why this happens is because air temperatures are warmer. As a result, there's more evaporation, hence there's more moisture content. There's more moisture content. The other thing that's interesting that actually happens is most of the dry air, or the driest air in the country, is over here in the desert regions of the United States. So areas like Reno, Nevada, Phoenix, Arizona, Denver, Colorado, these areas that are relatively arid actually end up being the areas with the lowest dew points. Meanwhile, again, the deep south and the coastal regions, much more humid. One of the things we're going to talk about in a future module is, if you notice, the dew point temperatures on the west coast are way lower than the dew point temperatures on the east coast. The air here on the west coast is much drier than the air here on the east coast. Well, the key reason why has to do with ocean currents. The ocean over here on the west coast is actually very cold. Meanwhile, the ocean over here on the east coast is very warm. We'll talk about how that relates to humidity in a future module, but just know, again, dew point temperature, the temperature that the air needs to cool to in order to become saturated. Higher dew point temperatures mean higher moisture content. Lower dew point temperatures mean lower moisture content. Now, the last thing we're going to talk about in this lecture is dew. As I mentioned already, Dew occurs when the temperature reaches the dew point. It cools down to the dew point. This usually happens at night. Why? Because at night, temperatures are coolest. And if it's clear, meaning there's a lot of radiational cooling, if there's very little wind, so there's no real evaporation, no real mixing happening, the air near the ground can rapidly cool. And then water condenses on the surface. Sometimes the temperature near the ground will be below freezing. And when that happens, we get what's called frost. Rather than condensing, the water vapor deposits. It goes from gas to solid, creating frost. So here's dew on the ground, and then here's frost. The last thing I'll mention is if you've ever noticed that dew is on the ground, but you don't really see any dew in the air, the reason why is because the temperature on the ground and on these surfaces cools the quickest due to radiational cooling. So the temperature right near the ground is much cooler than the temperature of the air even just a few feet above the ground. This is why we measure air temperature at eye level, because otherwise it would be influenced by the ground too much. And then again, on some mornings, if the air is cold enough and if that ground is cold enough, rather than getting dew, we get frost. Now in the next lecture, I'm going to talk about clouds and fog. Until then, thank you for watching.